Well, now in this video we will talk about the exercises from autocorrelated regression models, where we previous video we talked about autocorrelation regression models theories. Now we're gonna look into the implementation of the models and the estimations done in MATLAB and in R. First of all, to begin, before we begin, we need to just go through some backgrounds on some specific functions that will be applied in this chapter, maybe not much previously used, or will not much be used later. So first of all, the function Recursive, which computes a vector of autoregressive recursive series. So what is recursive? Recursive is for a sequence of A1, A2 to AM. Recursive formula requires computation of all previous terms to find the later term AM, which is an iterative process. For example, if A1 equals 3, AP, the equation of AP is 2AP minus 1 plus 5. So we will replace AP minus 1 with the 3. So A1 is 3, A2 is 2, 11, A3 is 27. A3 will use A2. So this is recursive. This is a series A1, A2. A vector A is created recursively. So what is the function? The function is a Recursive, which computes a vector of recursive series, where X is a matrix of dimensions n by k matrix, Y naught is a matrix of p by k matrix, A is p by k, and it returns 1 by n to 1 by k results, which contains columns which are computed recursively with results for Y naught for rows 1 to p. Okay. So the results equation is results j minus 1 to n into a1 to p, j minus 1 rows, all columns, 1 into 1 to p rows, all columns, and xj rows, all columns. This is what the results is. So how does it look? The equation Recursive for the function Recursive, how is it created? How does it look? Basically, first of all, nargin equals to 3. Now what is nargin and vargin? The two very important stuff we need to just remember. Nargin and vargin are two intrinsic functions in MATLAB. Well, nargin is number of arguments, input arguments that goes through. Vargin, on the other hand, is multiple arguments that go through, multiple inputs. When multiple inputs go through, that's vargin. So a very sweet example is with switch. Before begin in, what is switch? Switch out gives you output between different inputs based on the input. Very simple. So suppose you start with, it's kind of like a for loop command, but it's very specific logic expression, like switch expression, case expression statement, case expression statement. Let's look into an example. So switch nargin, here we want nargin to return number of functions input argument. So switch nargin, which is the switch expression. If function is C, we are creating a function add me, A and B. So you have two variables, A and B, that will be added in function C. So switch nargin, which is the switch expression, and case 2, well, you look into if there are two variables, the system will look into it. Case 2, if there are two variables, if you input two variables like add me 1 2, it will automatically add them up. If case 1, if you input one variables, it will add the same variable twice, otherwise it will give you 0. If you don't give any inputs, it will give you 0. So basically it will take the function margin and it will apply on A and B, the add me function. Another example is like simple switch expression. Switch n, case -n display -1, case 0 display 0, case 1 display 0 1, otherwise display other value. So this is the basic form of the case usage of case, which can be sweetly applied here. So if you now do add me 1342, it will give you added value. If you add me 13, then it will add 13 twice. So this is what is used in the Recursive function. So now let's go back to the Recursive function and see how it is using switch and margin and margin. So if there are three variables, wrong number of arguments to Recursive, it will equivalent or equal to exactly three variables. It will ask you, it will say that you have given wrong arguments. It will end here. Then n1 k1 is the size of x, as we know that x has a matrix of n by k dimension, y0 e has b by k dimension, a has p by k dimension. So if k1, the number of the size, the dimension of k1 equals dimension of k2, Recursive a y0 must have same number of columns. So you see k and k for x and y0, Recursive x and y0, they must have same columns. Oh, is not equals. So if margin is not equals 3, is not equals 3, then you need to give at least 3 variables here, because you have 3 variables, so you need to give at least 3 inputs. So if they are not equal, the columns are not equal, it will give an error, because we know that they are n by k and n by k, so k by k, k and k should be equal. If k1 is not equals k3, still you will have an error. If p1 is not equals p2, then you'll have an error, because there are the p dimensions are same dimension, they are not different dimensions. So first you fix the dimension, then you go to results. Results is a function which will create zeros for n rows and k columns. So for j equals 1 to p1, results is I. This is the first function, for loop function. For j equals 1 to p1, results I rows, all columns is y0 equals y0, j rows, all columns. So in results you will have all the rows from up to p1 and all columns. See, and then the second function is very simple. For j equals p1 plus 1 to a1. Now this is recursion is happening here. P plus 1 to in results you'll have x j rows, all columns. For k equals so there 1 to p1, so there are two for loops here. For j equals by rows, first of all you're fixing by rows, that this will be the size of the rows, and now you're fixing by columns. 1 to p1, j rows, all columns will have a k rows, all columns, because this is the equation we're following. Results j minus 1 rows, all columns, multiplied to a. Result, if it is y0, if we're talking about if you're talking about result, you're looking into previous one. See, ap equals to ap minus 1, ap minus 1 into a. So p minus 1, first we're talking about p minus 1, then you're talking about a into a 1 to p rows all columns plus then x exogenous variable x, which is j rows all column. So this is exactly what it is. A in a where k rows all columns into results jk minus 1 all columns by column. This will be set by columns. Results, first it will go through rows, the loop function, then the loop function will go through columns. Results j rows all columns. So first the MATLAB will look into all the columns, and the whole thing will happen for the rows p plus 1 to 1 up until n1. Okay, so this is the other function. So you have zeros n1 k1. You did two things. You first you included in results what will go in, that means y naught. Then you used y naught to create the rows and columns, and this function will give you a recursive series when you run the function, and that is important that we will use. Besides Vargin and Nargin, we are also we got ourselves familiarized ourselves with this, and there are many other ways to represent this equation, maybe much easier ways to represent this function Rexaler, but I think we will follow this as it is. Another way must be this. You see, in this another function that has been created, we have three inputs x, y, not a. It will construct a recursive series. We know the size, we know what will go into y equals x naught plus a1 t minus 1 apy t minus p. For t equals 1 to p, y equals y naught, well, p equals rows and columns, and but I think that is much more explanatory what we have done. So now the first problem that we intend to look into is this: simulating experiment, an AR1 regression model where y equals beta naught plus beta 1 xt ut. Well, ut is rho ut minus 1 vt. Uniform distribution, there's a uniform distribution over there that is fixed in repeated samples. The uniform distribution is fixed in repeated samples, and the parameter values are given. Then we find the asymptotic variance from this problem. Asymptotic variance is found, and that we show that the asymptotic variance is equals to mean squared error. So let's see what the problem is here. Simulate the following regression model with an AR1 disturbance term for t is equal to 200 observations. Okay, fine. So with beta naught is equal to 2, beta 1, these are the given information to us. The exogenous variable is generated from this equation, which is IID with n 0 mean 1 variance. Compare the simulated data to conditional mean of yt given by beta naught beta 1 xt. Simulate the regression model with MA1 disturbance term with the same information. Simulate the regression model with AR2. Simulate the regression model with ARMA 2 distribution. Okay, let us begin. First, we have to look into here. This is the okay. So let's see if we have local functions. We must have local functions. Oh, that's pretty easy. We don't have any local functions. We simply have the direct we're gonna go into simulation. First, you know, all equals true is all true list is equal to is rm remove object clear all clc graphics of random stream set global stream set seed 1 kind Marsana twister t equals 200. Then load the function and auto simulate. We are gonna put everything in a simulation function for our function. So t equals 200. Given parameters are beta 0 2, beta 1 1, rho, delta is given, sigma is given. Then we are gonna generate the exogenous variable. And what was the equation? 0.5t wt. So 0.5 into t wt, which is 0.5 t is 1 to t plus 100, because we're gonna do a recursive estimation here. So we'll create another additional 100 estimation because t is 200. So for optimization, the generally rule of thumb is the first 100 is less efficient, so we generally create another 100. Maybe we'll trim the first 100. Then a random t plus 100 rows and 1 column. It is added to this is wt and this is x. So 0.5 sequence is not only t, but this time sequence function will not only generate t random numbers, but it will generate t plus 100, which will be added to our norm t plus 100. Simulate a regression model with AR1 disturbance term. Simulate a regression model with AR1 disturbance term where v is well, exogenous variable has been generated. Now v is sigma. See, ut is not IID now, v is IID. From v will generate ut. Sigma into given, sigma is given to us, into random number t plus 100 rows 1 column, sigma r norm t plus 100. Then yeah, we are gonna simulate a regression model with the loop function. So u and y we are putting in loops. So we are creating, to store the data, we are creating u and y zeros. So replicate zeros. We're gonna do a very shortcut here. Replicate 0 t plus 100 times. So we're just gonna put in zeros in y and u. For I is equal to 2, remember all the summation signs we have discussed starts from 2 because s equals t equals s plus 1. So when s equals 1, that starts from 2. T equals I equals 2 to t plus 100. Beautiful. U is rho ut minus 1 plus vt. We know that ut equals rho ut minus 1 plus vt. Yt is beta naught plus beta 1 xt, beta 1 xt plus ut. So the equation simply rho ui minus 1 plus vi. This is recursion. It will continue to happen up until backward 100 times. It will happen backward 100 times. And yeah, yi beta naught beta 1 xi, it will go forward 100 times. Exactly the same thing here. T equals 2 to 100 ui 0 ui minus 1 vi. You see there will be a convergence that will happen. You will go 100 times up, well, ut minus 1 come down 100 times. So out of 1 to 300, your total range will always remain in, the total number of replication will always remain within 200. And so you have u and y generated with this equation. So y ar1, you are storing y here. So there you go. With AR1 disturbance term, you simulated a regression model. Now you need to simulate a regression model with MA1 disturbance term. Nothing changes. V again, we have to create V, generating random numbers, multiplying with random numbers. U and Y, storing. Now U equals Vt. Now the equation changing. Ut equals Vt plus delta Vt minus 1. Very simple. Yt remains same, nothing changes. Here we have the data. Now see, I told you that to overcome the startup problems, we generate 100 more, because generally when we are doing optimization type of stuff, we the first 100 observations might not be very efficient. So let's trim the first 100 now. So YAR1 starts from 101 till end rows. The first 100 row is not very good, not very efficient. And then YMA1, first 101 is not taken. Now how we are doing it in R, we're doing it much easier way. Instead of specifying the columns, we're just saying whatever it is, remove the first 101. In YR1, MA1, remove the first 101. X, remove the first 100. That's all. Mu is beta naught plus beta 1x. So we have mu equals beta naught plus beta 1x. Did we measure beta naught and beta 1? We know we measured u and y. Indeed, beta naught and beta 1 are given to us, right? So this generates mu because x is simulated. Now comes plotting the series. Again, plotting is not an issue. You can do it manually. If you have two series, you can just simply click in MATLAB and you can fix all these manually. You don't need to go through all these codes. I'm not sure in R. I have never tried plotting in R. Probably you'll need the codes, but R has a very nice structure for coding. So first you input X, Y and Y. You tell how many of the signs you want. This is the main title. Then in the X title you have expression of xt, Y title you have expression of yt, and this is just focusing on 40, 20 to 160. And the method is linear algorithm, lines x mu. Just like this, you create a subplot combining two different plots. That's all, nothing else. Simulated regression model. Now simulated regression model with AR2 disturbance term. Again, information is given to you, all right, and x is, again we need to generate the exogenous variable 100 times plus random number of t plus 100 rows, one column, so that the dimension match, right? V given to you, u naught is 0 0. Rho is, because now we have AR2 disturbance term, we have two equations, rho 1 and rho 2. Fine. See, I equals 3 length of v plus 1 y3. Because now t you have two rows, so it's not s plus 1, it will be s plus 2, because you have two coefficient correlation coefficient parameters. So because you have s plus 2 and s equals 1, so it will start from 3 up until to the length, so it will go up until 3. So ut equals vt minus 1 plus rho 1 ut minus 1 plus rho 2 ut minus 2. So this is u naught, I1 is vt plus rho 1 ut minus 1 plus rho 2 ut minus 2. Okay, just checking that if it is recording well or not, because show toolbar. So here you see example 7.4 has a ARMA 1-1 regression model where ut is yt minus beta naught minus beta 1 xt. We understand that vt is we are talking about ARMA. Ut is rho 1 ut minus 1 delta 1 vt minus 1, right? And AR1 MA1, if we have, I'm not sure if we have a AR2 here. Yeah, I think, but yeah, AR2 rho 1 ut minus 1 rho 2 ut minus 2 plus vt. this is the same equation that we are dealing here with here, vt plus ut. Okay, so I minus 1, ut minus 1, ut minus 2. Okay, so row is column bind row 1 and row 2, u0 is column bind 0, so you're creating a column with 0 0. You're creating a column with row 1 and row 2, one column, and for I in 3 to length of v plus 1, you have ut, you have vt, I minus 1, plus you have row. There are vectors, something is scalar here. Row 1 is scalar, that's why scalar multiplied to vector, we don't have the percentage sign. Row 2 end. So u0, whatever we have replaced with u0 will go into u. You have, and whatever we didn't replace anything with row 1 and row 2. Y will use this beta 0 and beta 1 x plus u, because of, very simple, because of this, why beta 0 beta 1 x plus u. And fine, I think x we have generated earlier randomly, and you have y created. Then you take fix for the startup problem. Very simple. Then simulate a regression model with ARMA 2. Now you have beta 0, beta 1, row 1, row 2. Things will be a bit more interesting here now. Again, x is randomly generated, R norm. V is sigma into random number t100 plus 1, we know it, and 0 sigma square. And then we are going to create a temporary variable, which is because it's ARMA 2, because this is ARMA 2, the temporary thing that we will have will be one column whose first two variables will be 0, because the AR part we are not taking. Here we are talking about the MA part only, not the AR part. So taking the AR part to be 0, and the autoregressive part and the moving average part we specify, which is 3 to end, because delta 1, delta 2, delta v 2 to n minus 1, 1 to n minus 2. See, this has an interesting structure. If you have two columns, 2 to end minus 1, the size remains same, but we have a shift up in delta 2, right? Delta 1, because what is the equation? The basic equation is, do we have ARMA 2 here? Let me go through it. Let me see if we have ARMA 2 example. No, we don't have ARMA 2 example, but yes, we understand what's going on here. There is a shift up. Okay, so we'll take all the rows except for the last row for v2, delta v2. I mean yeah, for delta 1, which is vt minus I. vt minus 1, see, vt minus 2. So this is vt, so vt minus 1 and vt minus 2. T minus 2 will trim the last two rows, but it will shift up one row. So 2 to n minus 1, 1 to n minus 2. You understand how the process happens? First of all, 3 to all, 3 to end, 2 to n minus 1. So first two rows are trimmed here. First one row is trimmed here, no rows are trimmed for the last one. Gives you a recursive structure, right? So this is temp, which is for the moving average part. Wind equals length of v, temporary d1 d2, only for d1 d2 is v3 to wind delta 1, v2 to wind minus 1 delta 2 v, very simple, to wind minus 2 v and minus 2. Temporary is u0. You're creating a column now, 0 0, first two are 0 and the third one is temp, this one, u0 cc row, everything else remains same. Now the loop function, 3 to length of tmp plus 1, right? Because we're talking about s plus 1, because this is the TMP part, the moving average part goes forward, it doesn't come backward, right? So u0 I rows 1 column is TMP I minus 1. Now this is the autoregressive part. Row 1 ut minus 1 plus row 2 ut minus 2. No difficulty here. So why is that gives you u equals u0? So TMP is the part created for moving average which will go forward at each iteration, not backward. Backward will happen for AR, autoregressive part, right? Very simple. Then the rest remains very simple. u0 TMP row 1, u0 I minus 1 row 2. One very important thing to remember is that always your arrays will come in third bracket. If there is anything, any calculation inside, that will happen in the first bracket inside the third bracket, and the loop function will happen in the second bracket. So you have ARMA 2-2 model, which is beautiful. You have a ARMA 2-2 Y model generated, which you can use for forecasting as well. Pretty good. Okay. Now we will turn to problem number 2. Well, let's just quickly go through the contents in the problem number 2. First of all, to begin with, okay, just spare with me a second. A dynamic model of United States investment. This exercise uses quarterly United States data from March 1957 to September 2010. Consider the model. Here DRI is the real income, is the real investment, while beta naught plus beta 1 real income plus beta 2 real interest rate plus UT, and because UT is not IID here, is autocorrelated, hence UT equals rho 1 UT minus 1 plus VT, where VT is IID. Yeah. Pass up screen recorder pro. No, I'm not looking for this one. Yep. Let me just quickly go through. Show toolbar. All right. So here DRI is a quarterly percentage change in real investment, RY is a quarterly percentage change in real income, INT is the real interest rate expressed as a quarterly percentage, and the parameters are beta naught, beta 1, beta 2, rho 1 and sigma square. Plot the real investment series and interpret its time series properties. Estimate the model by exact maximum likelihood using the full log likelihood function and the conditional maximum likelihood. Compare the parameter estimates with the estimates reported in table 7.1. Compare the standard errors using the Hessian and outer product of the gradients matrix test hypothesis. using LR world and LM. LM test based on the Gauss-Newton algorithm version, and the LM test based on root over t minus 1 R1, where R1 is the first order autocorrelation coefficient of the residuals obtained by estimating the constraint model. Now let's see what is suggested in the chapter that we have just discussed. Example 7.5, dynamic model of US investment. Here the log likelihood function, we're talking about full log likelihood using conditional and marginal distribution in it, conditional log likelihood and the full log likelihood function. So the log likelihood function of the parameter theta is twice pi log sigma square log 1 minus rho square minus u square divided by 2 squared 2 sigma square divided by 1 minus rho square at t minus 1 at t equals 1 log likelihood function, and for t greater than 1 it is v square divided by 2 sigma square. So see, instead of u square it turns to v square. So that was it. Let's look into the code now. We're talking about auto investment first, then auto test. So auto investment, here, yeah, let's see, the first thing to check if there is any local functions. Yes, indeed there are local functions, exact log likelihood function and conditional log likelihood function. By exact, I'm trying to say non-conditional, and conditional log likelihood function is the other one. So what in exact log likelihood function, the parameters are beta 1, b, the beta naught, beta 1, real income, real investment, real interest rate. Fine. So function of LF is equal to neg log BR. Inputs are these parameters, where beta naught in B1 is the first element of B is beta naught, the second element of B is beta 1, the third element of B is beta 3, beta 2, the fourth element of B is rho 1, the fifth element of B is sigma square. So all the elements are known to us. Basically B is what theta is. So first we need to look into U, which is real, so taking the residuals on the left hand side, we have real income minus beta naught minus beta 1, real investment, quarterly data on real investment minus beta naught minus beta 1 real income minus beta 2 real interest rate. This is the main equation. Then V is ut minus rho 1 ut minus 1. So trimmer u1 0 minus rho into trimmer u0 1. There is something I want to explain here. Whenever, suppose we're using the time series property of like u1 ut minus 1, then ut minus 2, something like that, here it suggests trimmer u1 0, which is meaning first we will trim the first row and nothing from the last rows, and in t minus 1 is we will not remove anything from the first row, but from the last row we will remove something. So if this is your full data set, removing the first row and nothing from the last row, which is ut, is this, and removing the last row but nothing from the first row is this. So you see, an important characteristic is whenever we are talking about ut minus 1, ut minus 2, ut minus 3, we'll start from the last step. It will go up just like steps, but the entire data, I mean at the end all should add up to the entire data. So you see how it is going here. ut ut minus 1, sorry, ut minus 1, ut minus 2, yeah. So this is ut minus 1, where we remove the last row but nothing from the beginning. Then if there is ut minus 1, ut minus 2, then we would have to go like this. So this is something important to remember, the structure of how we remove the rows. So ut, we remove the first row but nothing from the last row. We remove nothing from the first row, but we remove one from the, we remove the exactly nothing from the beginning, basically nothing, one row from the beginning, nothing from the end, nothing from the beginning, one row from the end. So ut minus 1. And the log likelihood function for t equals 1 is the full log likelihood function, which is minus half log twice pi minus half log sigma square minus plus half log 1 minus rho square minus 0.5 u square, well, u square minus 0.5, yeah, u square, whether this is u1, the first element of u, minus divided by sigma square 1 minus rho square. For t equals then for t is greater than 1, we use v, which is these two elements remain same, then minus 0.5 v square divided by sigma square, which was, yeah. So log likelihood function for t equals 1, log likelihood function for t equals 2. So basically now our log likelihood function is combining in columns both of these. So up until t equals 1, then greater than t equals 1, these two are the log likelihood function. Let's see how this thing is done in R. First, all true is all true, least equals is all true, rm remove object, which is simply alternative to clear all CLC, and graphics of. Then we load the package. We load with this function source, then exact log likelihood function. So in exact log likelihood function, the name of the function neglog. In this, the input of will go which are b ri ry ry rint. Yeah, these inputs will go in where beta naught, beta 1, beta 2, beta 3, beta 4, these are what mentioned. Third bracket is used. U again exactly the same, where because beta naught, beta 1, beta 2, these are scalars, so just multiplication sign is fine. Then trimmer u10, row trimmer u01. You see trimmer function is available for R2, so that's fine. The log likelihood for t equals 1 is nothing different than this, exactly what we have discussed. Here u1, the first element, we're accessing the first element of u, so we access the first element if u is third bracket, that's the only tweak. And then yeah, for t equals 2 to 3, and then we create a column with log ln L0, ln L1, and this function returns LF. This function returns LF and LF only, nothing else. So this is the first function. Then the second function is conditional log likelihood function. B r y r y r I n t, everything remains same. Beta 1 ri, beta 2 ri, well, trimmer. This is also exactly the same in conditional. Basically in conditional log likelihood function, we are not talking about t equals 1, we are starting from t equals 2 to 3, so just separating the function 10 other functions. That's all for optimization instead of combining the functions. So just v sigma squared. This is conditional log likelihood function, and then we are returning LF. That's all. That's very simple. Then we are going to use these two functions into our model. Well, we are creating a function called AutoInvest. Inside the function we will run the stuff. First we need to load the data. In data read table, this text file will go into this. Well, first column, all elements in first column is CPI, all elements in second column, just a third bracket comma 2. Very simple. In our GDP, the all elements in third column is invest, then 10 years interest rate, 3 years interest rate, T-bill. So all these are coming in. Then generating the variables data that's starting in 1958 quarterly 1, GFC is zeros, length of US invest minus 13 rows, length of US invest minus the 13 rows, and one column. Then once 13 rows, one column. Okay. I'm not sure what GFC is. Okay, so we are creating zeros here, which has the I mean, here we have the US invest length minus 13. Very simple. We don't want last 13 well, investment information. Zeros up to that, 1 and ones, another. Okay, so minus 13, and this will go into ones because it's column. The rest 13 is just ones. That's what we want. So we're doing column bind, where first first portion of the column is replication of 0, number of rows in data, minus 13, then replicating 0, number of rows, replication 1, 13 times. The whole thing will go into column. Then real income is 100 into log trimmer, invest divided by CPI. Yeah, this is not regression. Invest divided by consumer price index 10, log trimmer, invest divided consumer price index 01C. This is in T, this is T minus 1. Just like before, going up in steps. Log trimmer, invest CPI 10 minus log trimmer, invest CPI 01. So here no element by element division is going on, remember that. Then INF 100 into log trimmer, CPI 10. Again, this is also in in lags. So this is the first data, then this is the lagged value. UT minus TT minus 1. Very simple. CPI 10 trimmer, CPI 01, INF. We don't have, remember, anything going element by element. Then RI and T streamer are 10 years quarterly divided by 410 minus INF. Okay, fine. Real income is streamer GDP divided by CPI. This is also in lags, something we just discussed. Streamer GFC 10, so that it reaches the same size as the others. Then we do OLS regression. T is the length of real income, Y is real investment, X is ones. Always it will come as ones, real income and real investment. This is the equation. So T is length, Y is real income. Then we do column bind, replicate 1 T times real income, real investment, then regressing X on Y, linear model of Y regressed on X, minus 1 of this thing. We're just taking the coefficient. Y error is x minus y minus xb, so mean square is the sigma. So whereas then we're doing exact maximum likelihood estimation. Well, theta naught is b 0.02 and square root of sigma square. So with OLS, what we did is that we found the initial values with OLS, that's all. We also find initial values with OLS. The value of rho here we're using 0.02 because we have not found anything for the rho. Probably nothing is given for the rho in the question too. So we're taking because in the question it says compare the permutation estimate reported in table 7.1. Rho is there, so we are taking rho 0.02 square root of sigma square. This is initialization, that's all. Then theta Hessian and Fe is the function estimate. So if in concat we are estimating P P neg log P is beta basically at P neg log P dri dr. This is just to show you that instead of writing V we can go with P, but the function will still bring estimate beta int theta naught. So optimization theta naught, first is theta naught par value which it will update. Then neg log, then ri equals dri, ry equals dry, rint equals rint. This will how the data will be presented, where the data will be saved actually. Method BFGS Hessian true. We want also the system to give us Hessian. And inverse of Hessian is simply inverse of Hessian. There's no tricks there. So theta is in par. If he is value will be saved as value, H is saved as Hessian. That's all. So results for exact maximum likelihood starts with an n, ends with an n. Concatenate and display starts with an n, ends with an n. Negative log likelihood function, very simple. And standard errors starts with an n, ends with an n. Okay, and display theta, diagonal inverse of Hessian. So parameter estimates is unnamed column bind theta, diagonal estimates of inverse of Hessian divided by t. Unnamed. No, I'm not sure what unnamed is. No, I don't think there is anything called unnamed. Okay, so conditional maximum likelihood estimates basically are just removing the names. It's kind of like that if you're talking about that. Okay, then conditional maximum likelihood estimate, we're gonna estimate this as well. same in the same way. Neglog C, nothing else, no changes. And then we are gonna, in the same manner, we're gonna express it. So they see if there's anything for unname. Remove names or dimension names. Unname is simply to remove the names if there is any name associated. So that's what you understand. Anyone would understand. Looking into this command is function. So unname. Remove names. Okay. So this was US investment example. Pretty simple. Yeah. Then the third one. Then we do LR Vault and LM test on this problem. So let's move into auto test. And how is this different? It's the same thing. We are coming up with two functions. Fine. No changes. To get inverse streamer and to be able to use these functions, inverse streamer, numeric gradient, we load the library from MATLAB. We load the MATLAB library, which is great. A good computational specialist or a good mathematician always work in multiple packages. You can be very specialized in one package, but you cannot always disagree that one package has benefits that surpass the other. So it is always good to work hand in hand if you in both the packages, because a lot of functions come handy like this R and MATLAB. In fact, there is something to add here, that is MATLAB while being very useful, because you can have a strong, you can do the dimension control in MATLAB is really very strong, and for econometricians that is an absolutely important thing to do on a regular day basis. On the other hand, R, because of its wide usage, is well integrated into many software. Like you use R to convert an output data from SAS to Stata, or you can use R simultaneously with Stata, and probably with MATLAB too, which are really good. And as you can see, both the languages are very reflective of each other in terms of contents. So I don't see any I think it is good to work with both together. So we are loading the MATLAB library here, then we are mentioning the functions just like before. This was not necessary. Basically return minus LF could have been fine, but yeah, let's do this. Constraint and unconstrained, everything remains same, nothing else changes here. We get the data, we do the regression, OLS regression, so that we get the initial values that we can use for optimization. Estimating our parameters with maximum likelihood estimator. So unconstrained. Now in constraint model we don't have row. In constraint model we don't have row, which is not t equals 1, it starts from t greater than 2 or rest. So in constraint model we don't have the row, that's all. And so LR test, which is constraint minus unconstrained, log L naught minus log L1. LR test, well, concatenate and display, suggest LR, and the second one is p values. 1 minus CDF, cumulative distribution function, that we use chi-square on LR. Under this function we're running that we use chi-square under LR. 100 minus, this is the percentage confidence level. We are actually finding the confidence level. So cumulative distribution function using the chi-square method on LR with 1 degrees of freedom. 1 degrees of freedom. So chi-square LR 1 degrees of freedom. That's all. 1 minus p chi-square. Instead of CDF, we are saying p. For chi-square it has a different function. You see, CDF can have different method. We just have to change what method we want here. But here, on the other hand, in R we have a different method for chi-square. So 1 minus p chi-square. Fine. LR test and then world test. We are constraining what? The autocorrelation coefficient, so we put 1, and we are changing again, we are checking against if the autocorrelation coefficient rho 1 equals 0 or rho 1 is not equals 0. That's all. So Q will be 0. This is row bind, this is coming in rows, so we do row bind coming in rows. 0. Then basically these are different elements that we are presenting in row bind. So first create the vector column in column. They will be coming in column. Now you are converting them to row by row bind. And t into r theta minus q, r theta 1 minus q, because this is nothing is scalar here, both are what should I say, both are vectors here, because theta is also vector. So r theta 1 minus q multiplied to inverse of r into inverse Hessian into r transpose, inverse of r inverse Hessian into tr. Then it's very simple. Basically R is very simple. You don't have to think about signs while you're dealing with R. We don't have to think about signs at all when we are dealing with R. Then r theta minus r theta 1 minus q. So basically this is it. And again 1 minus p chi square. Then LM test. So theta naught, we want LM test on the first 3 elements, and 0 and theta naught for obviously beta 1, beta 1, beta 2. 3 elements, then row. You see beta naught, beta 1, beta 2, 0, then beta 3 sigma. So see theta naught, we are representing everything in a column. Then Gmat is numeric gradient, because we are using the MATLAB package with log LT theta numeric gradient. So Gmat is numeric gradient. Then G is mean of Gmat transpose. This is much difficult. Column means of Gmat. First we are finding column means of Gmat, which is in column. Then we are doing the means in column bind. So representing in column bind. So well, mean of Gmat. And then this one is easy. This is the only tweak. This one is easy, just transposed Gmat multiplied to, it is the decomposition. Then T into G inverse, G transpose inverse of OPG into G, which is the LM thing. And then we just look into, you know, LR world and LM test. We just look into well, the probability distribution. All the parameters are statistically, so our results suggest all parameters are statistically significant. at 5% level. Test, we wanted them with a Gauss-Newton version which uses maximum likelihood estimation. We did that, and we want one LM test based on root t minus 1 r1. So first step is to do OLS regression for the initial values. So we do OLS regression, find the initial values, and then we find r square coefficient of determination, which is 1 minus y minus mu of y transpose, basically y minus mu of mean of y square divided by u square, or this we can write as 1 minus mean of y transpose y minus mean of y divided by e transpose on e, right? So first we do a basic regression, then r1 beautiful. Okay, so autocorrelation function, this is autocorrelation, right? We just run a thing called autocorrelation function in our SCF function. We run the autocorrelation function on u. We don't want a plot on u for with one lag. Autocorrelation function on u with one lag. Let's see. Oh no, sorry. Yeah. So autocorrelation, autocross covariance and correlation function estimates x one lag on u, right? So that's what it says, one lag on u. So instead of writing the whole thing, the whole autocorrelation function, we can just simply do an autocorrelation function, run an autocorrelation function, and in R1 we can store the autocorrelation function elements, and then we do lmt minus 1 R2. So the second element of R1 is squared. Here this is, so this is done in two steps. We needed to estimate autocorrelation function and we needed to square it. So we are simply calling autocorrelation function directly in R. With u1 plot, we don't want to plot, and we want autocorrelation function element only. So you have R1 and we want the second element to be squared. That's all. Then p square lm1. So we all the parameters are statistically significant at 5% level, and we have correlation coefficient. So LM test first order autocorrelation of residuals. Oh yeah, we have that for MATLAB 2. I'm sorry, this was what we were talking about. 1 minus LM, so ET transpose, we break it down into E, then T transpose, exactly same thing. Then R2 is 1, R2 is T minus 1 into R square. Here R2 is regression, we're doing regression of y square on E square, CT y. Fine. Then first order autocorrelation of residuals. Then we find regression of x on y. Then you have u, and then we do autocorrelation. We run autocorrelation function for both. Autocorrelation of u10, u1, exactly the same thing as you can see, and lm t minus 1 R1, so t minus 1 R2, and t minus 1 r1 second element has been squared root over t minus 1, because we're looking into root over t minus 1 r1, where r1 is the first order autocorrelation coefficient of the residuals obtained by estimating the constraint model. Okay, root over t minus 1 r1. So when you bring both of them together, lm and yeah, first order autocorrelation of residuals. You okay, because nothing in the first element, because we're no, this is lag, number of lags. Okay, fine. 1 minus, because autocorrelation is happening in the second element as we have discussed earlier. Okay, so this is auto testing, because basically this program ends when we were talking about test. Rest is simply autocorrelation function estimation, which is really important as well, residual autocorrelation, and we want to see if there is any autocorrelation or not when we do chi-square estimation. Thank you. Right. Now let us talk about the third problem. The third problem is asymptotic distribution or auto distribution. We're going to consider this model where y equals beta naught plus beta 1 xt plus ut, and obviously ut is autocorrelated, the residual is autocorrelated, hence vt on the other hand is iid, so ut is equal to rho ut minus 1 plus vt, where vt is iid with n 0 means sigma square variance. Here the exogenous variable xt is a deterministic variable generated as x with uniform distribution minus 0.5 to 5, and the population parameters are given to us. Simulate the model for t equals 500 observations and use the expression in equation 7.26 to compute the asymptotic variance of the conditional maximum likelihood estimator of beta 1. Compare the result by computing the maximum MSE of beta 1 using a Monte Carlo experiment with 5000 replications. Use the 5000 simulated values of beta 1 calculated to compute the standardized empirical distribution of beta 1 hat and compare this distribution with a standard normal distribution. And we need to repeat the part B for the maximum likelihood parameter estimator of beta naught in the model. So let's see how this was done in the chapters theoretically. Obviously in theories we are talking about deterministic, when x is deterministic. Here was the problem we have already discussed. Here x minus rho xt for 500 simulations. This was the parameter. The asymptotic variance of beta 1 hat is the asymptotic variance is sigma square divided by x minus rho xt minus 1 whole square, 57.4. So this was the asymptotic variance. The model is simulated 5000 times with conditional maximum likelihood estimator computed at each application. xt is deterministic and it does not vary over replications. In case of beta hat, the mean squared error is 1 by 5000 to replications, beta I minus 1 whole square. So is this, which agrees with theoretical distribution, and normal distribution is beta 1 minus 1 divided by the mean squared error. So deterministic exogenous variable, what was the theory that we discussed in asymptotic distribution? When we were discussing asymptotic distribution, what equations would we need? Basically the AR1 model consists of G1t, G2t and G3t. So you see v xt rho 1 xt minus 1 by sigma square. V is sigma square's element is beta 1 element, v ut minus 1 or rho 1 element and sigma square element, and simply the sigma square element. Taking conditional expectation of g1t, we have 0. Oh, this is just proving that taking conditional expectation and updating how well. This was a proving problem in distribution. What we try to prove here is that gradient g t theta vector satisfy the conditions of martingale difference square. So root t theta hat minus theta 1 okay. Deterministic exogenous. Whenever we're talking about deterministic exogenous variable, the information matrix I11 is limiting property of x minus rho naught xt minus 1 sigma square t minus 1, which yields the proximate variance beta hat, which is sigma naught square divided by x minus rho naught xt minus 1 whole square, or which is 1 by t minus 1 inverse of information matrix. This is something you're going to use now. So let's see. We are talking about auto distribution. Let's just to begin with, first, if we have any local functions. Yes, we do. So first, because we're gonna do 5,000 replications, we're gonna do Monte Carlo simulation, so we need to set the simulation property. All true is all true least is equal to is all true. RM is remove object, graphics off. Then set.seed 1 2 3 4 5 type a kind Marsana twisted. Very simple. Then helper function for figure, for inverse of inverse function, and for Rexar recursive estimation. We need to load this package emtsutil. Now let's look into the local functions first. We need to do a log likelihood function, exact and conditional log likelihood function, because the questions need us to estimate maximum likelihood estimator. Conditional maximum likelihood estimation, simulate the model to compute the asymptotic variance of the conditional maximum likelihood estimator beta 1, and what would be for the maximum likelihood estimator of beta naught. So exact and conditional. Exact, we have beta naught y and x. Like log e, we have beta y and x. Okay, fine. So beta naught is first element, beta 1 is second element, rho is 10h, b3. This is very important to remember. Why are we putting a tangent function and restricting our parameter with tangent function? Let me show you. Let me show you. So suppose we have a parabola, or in all kinds of iteration, we will need to basically we will continue to do this, because suppose this is an estimation we want to reach, which is you have two variables, response and predictor. Well, this is a predictor variable, or y, and you want to have the estimated parameter within a restricted tangent function, so that basically with each iteration if this is your population parameter, your sample parameter gets close to the population parameter. So if you have a response and a predictor variable, you want your response variable to eventually with after each iteration converge to the predictor variable estimations, so that in convergence you reach your desired forecasts objective. So basically this is why we put a tangent function, because, well, then the beta parameter will not become an outlier. You see, will not simply wander away. The beta parameter will remain within a restricted tangent function, or in other case is called a rational transfer function. Different kind of rational transfer function is used in econometrics. Tangent function is used more. So so this is the purpose of putting the tangent function. Hope you understand. Without putting the tangent function, the estimations will wander away. With putting the tangent function, there is a restriction that the estimations are located on the parabola. Okay, so rho, we want our correlation coefficient to be within the tangent within restricted parameter. Sigma square is absolute value of beta 4, and 1 minus rho square is, well, FAC 1 minus rho square is the factor, probably. Yeah, so u is equal to y minus beta naught beta 1 x, fine. Then v is equal to trimmer u1 0 rho 1 trimmer u0 1. We know why we do ut minus rho 1 ut minus 1. Very simple. How do we do it? We don't need trimmer in R. We can simply do u to the u in the element minus 1, which means we remove the first row and row u length minus length of u, which means we remove the last row minus length of u. So minus 1 removes the first row and minus length of u removes the last row, and then 0.5 log twice by the exact, because it's exact log likelihood function, we want everything together. Basically 1 minus rho square, sigma square divided by 1 minus rho square was the full log likelihood function basically, and so this remains. Okay, 1 minus rho square. So we have what in exact, we're talking about exact, we have 0.5 log twice by 0.5 log sigma square. So this is exact log likelihood function, which is the full one. So in the full one we have conditional and the marginal, both portion. So first, to begin with, we have the full one, the non-conditional, then the conditional added together. That's minus log sigma square minus 0.5 log 1 minus rho square, which is that, and u square divided by sigma square divided by 1 minus rho square. 1 minus rho square is the equation, as we already know. If there is any confusion, just have a look. In 1 minus rho square is the denominator element, you see. So in all information metrics, 1 minus rho square to 1 minus rho square sigma to the power 4. All right. So log likelihood function at time t. From previous example, this is exactly the same thing. 1 minus rho square u square divided sigma square divided by 1 minus rho square. This is log likelihood function at time t equals 1. Log likelihood function at time t is greater than 1 is v square by sigma square, and then log likelihood function is the both together. So this is exactly what we did before, exact log likelihood function. No changes at all. Then the conditional log likelihood function is just the second part. Taking the second part is the conditional log likelihood function. No change. The only thing is that we previously, in the previous example, we had our row to be fixed, which is 0.2. Now in this case our row is not fixed. We are allowing our system to estimate our row, but within a restricted line. The row should locate within a restricted tangent line, basically. So the row will be located in a manner that the slope of the response and predictor will be almost converging if you run iteration. So that's what the only changing part compared to the previous one. Nothing else is changing. As you can see, C is the column of TMP and TMP1, where we don't have TMP1 and anything. Everything else remains as it is. Inside, when we are accessing the arrays, we give third bracket. Otherwise, all the without accessing the arrays, we are bringing in the entire vector with first bracket. That's all. The whole game is within first and third bracket for R. In case of MATLAB, it's not true. Now let's do the simulation. So auto distributions, first set the parameter values. We have been given some values for our parameters. We set them. We set the starting values, which is theta naught. Our number of simulation is 500. Our number of observations is 500. Replication will be happening 5,000 times. Options obtain set, large scale of display. We want our iteration to be displayed until final iteration reaches. So we want our system to display the final iteration only, not the entire process. If you put iter, then it will show all the iteration. That's all. You don't need to do options in R, because R runs options directly. Now we have recursive estimation, or a Recursive function will run the Recursive function. If you can recall, Recursive function gives you, the Recursive function computes a vector of autoregressive recursive series. So it gives you a vector of autoregressive recursive series. It generates randomly autoregressive recursive series. So simulate a regression model with AR1 disturbance term, autoregressive recursive series. We want to simulate that. So first, because X is fixed in repeated samples, we are talking about deterministic exogenous variable. T rows 1 column minus 0.5. We are just fixing X with minus 0.5. Minus 0.5 because our distribution should be uniform distribution with mean minus 0.5, variance 0.5. So minus mean, this is just the mean. So random T1, not normal distribution but uniform distribution, random T1 run if T, we don't have to set the column, just T, it will automatically do. By default is column as 0.5. Then let's do the conditional one. Exact is the same thing. First do the conditional estimation. We have set the arrays for the values. condition is zeros, number of draws, rows, one column. That means we want condition to have 5000 vectors where the simulated results will, the replications will be stored. So in draws 1, I think condition array, the function will be array. We want zeros of n draws and one column, with a column of n draws and one column. So this is not important. Text bar, text progress bar, 0, maximum e is number of draws, style is whatever style it is. For k is equal to 2 to number of n draws, because we remember s plus 1, and s when you progress is s plus 1 time t equals s plus 1, and when s equals 1 then 1 plus 1 2. So 2 to number of n draws is equal to, well, this is the equation, square root of sigma square into random number. So we are with a random number we are generating v first. So square root of sigma square is multiplied with a random number of t rows, one column. Square root of sigma square r norm, not ranif, r norm t, for k is equal to n to 2 draws, for k in 2 to n draws, 2 to n draws. U is equal to, now recursive series, we want u to be a recursive series, rexr and v, then square root of 1 by 1 minus row square multiplied to v1 row 1. Let's see what was the rexr function inputs. So for rexr, a matrix of dimension v, which is x, instead of x we put v, instead of y naught, rexr has x, y naught and a matrix of, so n by k dimension v, which is a matrix of which is x exogenous. So here is v, then instead of y naught initial value we use square root of 1 by divided by 1 minus row square. Obviously divided by 1 minus 1 by 1 minus row square is coming from the information matrix I22. Let me show you. One divided by 1 minus row square, which is the second derivative, limiting property, second derivative of log likelihood, second derivative of the autocorrelation coefficient on the log likelihood, 1 minus row square, very essential. So 1 minus row square, which is multiplied to v, so that it gets the size of v, it generates the size of v. This is y naught, and then a, x, y naught and a is row 1, which is the correlation coefficient. So generally things happen like this: if a1 is equal to 3, then ap is 2, a to p1, p minus 1 plus 5. So if a okay, p minus 1 plus 5, so plus 5 is this, the last element, plus 5 is this. If your equation is like ap equals 2, so if your equation, suppose you have a1 equals 3, then a2 equals 2a1 plus 5, then a3 is equal to 2a2 plus 5. So this is the plus 5. All right, a1, a2, a3, these are all rows, row 1, 2a1, 2a2, 2a3, and x is this. So the 2 is v. So 2, the a's, and 5 is this, right? So u rexr v, then square root of 1 by 1 minus row square multiplied to v1, and then row 1, x, y naught, a, and the equation will be well, the equation will be y naught equals a xt minus 1, something like that. Yeah, so basically it's easier to remember the way I just explained. A1 is equal to 3, A2 is equal to 2, A1 plus 5, A3 is equal to A2 plus 5, something like that. The recursion will happen. This is the recursion way. X A y naught recursive estimation, and y is equal to beta naught beta 1 x plus u. Now as you have u generated, I mean the recursive series for u has been generated, you have u. So the only thing you need to remember is our residual for u is v here, and yeah, our residual for u is v, and our x is v, and this gives multiplied to v gives us exogenous variable. This is generating the exogenous variable basically, or the other way around. If this is the exogenous variable x y naught, well, this is depending on x, this gives you y naught, right, which is generated based on x, and then rho 1 is the correlation coefficient a, which comes in between. Okay, so in R Rexorder, we run the Rexorder because we load the package already before. Column bind, we want v to be in columns, then column bind square root of 1 divided by 1 minus rho square, minus rho square multiplied to v1. Fine, the first element of v has multiple elements, I'm not sure, probably yes, so we are taking the first element of v, only the first element of v, okay, because rho will continue to change. No, rho 1 is fixed. Okay, so this is fixed, see, this is constant, and v itself is no, v is not constant, this is constant, y naught is constant initializing, v is x, which is a vector, and then column bind of r1, and then column bind rho 1, which is also a vector, then beta naught beta 1 x plus u. Okay, and then we for k is equal to 2 to n rows, we specify, we generate randomly v u y, and then we do run the function tmp, where we have after running the function neglog c, conditional function is run with fn in on with beta inputs of tim theta naught c neglog c, then y equals y, x equals as method of, so BFGS Newton-Raphson algorithm is used, and TMP has the par results, thetas are updated. Now is important thing is, now after that in condition where there were zeros, condition which up to size k, we include the TMP, whatever we estimated, we let it store TMP results, right, which is TMP2. With TMP2 py function values, are we looking for the function values? I think so. Our question suggests that we are looking for variance of the, okay, so we want, but that's over computing a better one using maximum likelihood estimated conditional asymptotic variance. We want the TMP2 to be generated 5,000 times using a Monte Carlo simulation with 5,000 replications. So we're comparing mean squared error. p yx. In p what we do, we have beta naught. Let's have a look into the function. Beta naught, beta 1, sigma square, no, beta 1. Okay, we are estimating beta 1 here. Okay, so TMP2 beta 1 will be generated 5000 times for up to k, and then it ends, the loop ends, and it will continue 5000 times. The whole calculation will continue to happen for 5000 times, continuing to store beta 1, and you will have 5000 beta 1 replications, which is really nice. And set text progress bar pb k, pb up to k, and close pb. So we start pb and we close pb. Done. Then we do mean squared error, which is 5000 conditions minus beta 1 that we had squared. The whole thing is squared in and there is the mean squared error will have another 5000, a line of 5000, a plot of, I mean, it will give you a series of 5000 studies and 5000 results, which checks the difference between beta 1 estimated parameter minus beta 1 given beta 1, and sum of squares is sum of trimmer x10 row 1 trimmer x01. We have x generated earlier, 500 row 1 trimmer x01 xt row xt minus 1 squared, simple, xt minus row not xt minus 1 squared, sum of squared errors, because this is the denominator. Yeah, minus 1 squared. See, this is the I beta is SSQ divided by sigma squared. I beta is information matrix is sum squared error divided by sigma squared. That's all. Information matrix of beta. Sum of SSQ is sum of x minus 1 when we are removing the first row, minus row into x minus length of x, removing the last row, squared. Asymptotic variance, we have the asymptotic variance. That's all. And then we can generate the graph. We can do it manually. Okay, par z condition minus beta 1 divided by square root of the condition minus beta 1. Condition is 5000 replications of beta 1 estimated minus beta 1 divided by square root of mean squared error is z. Okay, and then we just bring them in together. X lab, y lab. So histogram of z, we want a histogram of z normal distribution. See, estimated 5000 replications minus beta naught divided by root mean squared error, and then we just draw a graph with this. Compare this distribution with a standard normal distribution. So that was it. One thing very important that we did here in this example is that we use the Recursive function. Recursive function takes input of x, y naught and a, and suppose you have an equation structure like a1 equals 2, then a2 equals 2a1 plus c or plus 5, then a3 is equal to 2a2 plus 5 or something like that, which, well, 2a1 plus 5, then 2a2 plus 5, right? What will change here? A's will change, right? And who is represented by a? Here we are representing A's with the last element of the inputs, which was in our Recursive function, that was a row. the correlation coefficient. Indeed, you see 2a1, 2a2, all these are correlation coefficient. They will change the relationship between y and x. And then we have y0, which is kind of fixed, because y0 is 1 minus 1 divided by 1 minus rho square square root, that is multiplied with v1, or basically y0 is simply v square, y0 is simply, or this is x0, I guess, vt divided by 1 minus rho square. This is the variance, the asymptotic variance here, which is, we dealt with this before, the asymptotic variance. So here we need to remember u is a recursive series of v is u's residual, so the variance is v square, y0 is v square divided by 1 minus root over sigma square. 1 minus sigma square, we're taking a root on the entire process, so v1, the whole thing is multiplied with the first element of v1, and that is y0, which is kind of fixed, which doesn't change, because v doesn't change, v remains same. But x, you see, y0 is changing. y0 has the size is p by k, which should also be the same sized as a. The dimension of these and these should be equal, so we allow rho 1 to change, so that this whole estimation y0 has the same size of a. And x is different, x is n by k, and so we put v here, the main variable, the main exogenous variable here. So that's all. That is the only tweak. Another important thing we did in this example is that instead of using a fixed autoregressive autocorrelation coefficient, instead of using a fixed autocorrelation coefficient, we allowed the system to estimate the autocorrelation coefficient, but with a restriction. So that concludes the next problem. The following problem is sample mean, and the first thing to check is that if we have it in our theory. Interestingly, in this efficiency of the sample mean problem, this is an efficiency problem. This is what we are doing. You see, efficiency is that when we have a relative, we measure relative efficiency. Basically, OLS, we remember OLS has several limitations, but over maximum likelihood estimation, but we can remove some of the limitations of OLS by quasi maximum likelihood estimation, and quasi maximum likelihood estimator, which is this equation. Beta hat least square is OPG beta naught divided by information matrix. So which was first of all sigma square divided by 1 minus rho square x square, then 2 xt plus 1 rho naught I divided by x square. So how did this come? I beta naught is x square divided by sigma naught square, or xt yt minus xt transpose yt minus beta naught xt whole square OPG. We're doing OPG now, divided by sigma naught square, or we take it out and we have x square plus 2i equals 1 to t minus 1, t equals 1 to t minus I, xt plus I, rho naught I. Okay, these are the elements where we saw that information matrix and the OPG, they don't equalize, they are not the same. Information equality does not hold for OLS, so it gives us misspecified information. We want them to equalize, hence we combine them in our expression of OLS variance, which is sigma naught square divided by 1 minus rho square. Sigma naught square divided by 1 minus rho square remains as it is, sigma naught square 1 minus rho square. We just combine them. This one comes below, this one comes above, and these also rearranged. We have this equation, that is quasi-maximum likelihood estimator. Now when we take the variance, beta hat least squares variance is represented like this. We divided that with regular variance of beta hat 1 minus rho square x minus rho naught x t minus 1 divided by 1 minus rho square, 1 by 1 minus rho square vt, remember, because here it's supposed to be vt. So when we express it like this, if it is greater than 1, the more it is greater than 1, the more loss of efficiency. So efficiency of y but in the presence of autocorrelation was if x equals 1, which is fixed. Beta represents intercept. The OLS estimate of beta is the sample mean. Asymptotic variance, OLS estimate of beta b is the sample mean and the asymptotic variance of beta hat least square. And variance beta hat least square is 1 by t square sigma naught 1 minus rho square. From here actually we don't have any x's because we don't have any x here. Wait, is sigma square divided by 1 minus rho square. This element is gone, it's not there. Obviously the other element will not be there, so 1 plus 2 I equals 1 to t minus 1, t equals 1 to t minus I, rho naught will be remaining only, or sigma 1 minus t 1 minus rho naught square minus 2 rho naught 1 minus. This is what Harvey in 1990 suggested. We don't have any x's here. 1 minus rho naught square 1 minus rho naught square 2 rho naught 1 minus rho naught t, setting xt equals 1. So without xt, this is it, and setting xt equals 1, this is what we get. Rho square 1 minus sigma square divided by 1 minus rho square, or sigma naught square divided by t minus 1 1 minus rho square using maximum likelihood estimator, right? So now we have the efficiency ratio of without x and with x setting to 1, and upon taking the limits, this is what we are left with. This is what we are going to do in this problem. In this problem we are going to consider the model and we're going to prove this equation, right? And the Harvey's equation, this is the Harvey equation. Verify the result computing the left hand side equals to the right hand side. Give an expression for asymptotic variance of beta hat for the conditional maximum likelihood estimator, and asymptotic for ordinary OLS. So conditional is asymptotic variance is the we are gonna simply do an efficiency test with these two comparison. Let's question part B and C. Assuming property parameters of beta rho naught sigma naught sample size t 50 so whatever. Let's look into this. Our problem is called auto mean. So this is auto mean. Is there any local function? No, I don't think there is any local function. I think this is a quite easy program. So list is all equals true, is all true, list is equal to is all true, rm remove object, then graphics is off, then set dot seed 1 2 3 4 kind Marsana twister, then our row is given 0.6, sigma square is given 50 t. You see these informations are given to us. 0.6 sigma square 50 and sample size is t 500, which we represent in a column. Now first we do OLS, okay, with in a recursive manner. Why do we need a recursive OLS? Because the question asks us to, I guess. So for k is equal to 1 to length of t, so we have different lengths, that's why we have different lengths suggested to us, 5 50 500 blah blah blah. For k is equal to, for k in sequence of t, Okay, is equal to 1 to length of t. First t, first k, tk will be stored in t, so we will know how much, how many or what is the k value for us. That will be studied here. Basically 550, 500 all are in column t, so the elements tk, 5, 50, 500 will get three results, right? Sum is 0 for I is equal to, by rows, for I is equal to 1 to t minus 1, j is equal to 1 to t minus 1, because y I is equal to 1 to t minus 1, I is equal to 1 to t minus 1, t is equal to 1 to t minus I. So by rows and by columns, the equation suggested by rows and by columns, because the equation was suggested, so because the original equation was I is equal to 1 to t minus 1, then t is equal to 1 to t minus I. So j, I and j, 1 to t minus 1, then j is equal to 1 to t minus I. Then sum of, we are taking sum of sum plus row 1, sum is 0, so that it iterates. Sum is the sum plus row up to I. What j is equal to 1 second t minus I, sum is sum plus row I. Have we mentioned I? And obviously t minus 1 row I. Okay, fine. This was the equation. Sum of sum plus row I. Sum plus row I. Sum is 0, sum starts with 0. End. Then OLS variance is sigma square. OLS variance of OLS is beta at least square is sigma square t plus 2 sum, sigma square t plus 2 sum divided by 1 minus rho square into t square. Okay, fine, very simple. This is the sum thing. This is the sum part. So sum part, well, it's t plus 2 sum divided by 1 minus rho square sigma square. Now let's do it on the basis of Harvey. What did Harvey suggest? This is Harvey's suggestion. Okay, this was what we did. This is Harvey. Sum of h is t into 1 minus rho square, t into 1 minus rho square minus 2 rho 1 minus rho naught square divided by 1 minus rho naught square divided by 1 minus rho naught square. This is sum. Then we'll use sigma square sum of h, sigma square sum of h divided by 1 minus rho square t square. Okay, this is the Harvey equation presented with this. There is no element by element operation in none of them, so they kind of converge. Now OLS estimator based on asymptotic variance is one with Harvey, one without Harvey, and MLE variance. Variance of maximum likelihood sigma square t minus 1, 1 minus rho square. The regular maximum likelihood estimation 1 minus sigma square 1 minus t minus 1, 1 minus rho square. That's all. So we have the different variances. Okay, fine. One is without. Basically what we need to do is that if we divide OLS with OLS Harvey, oh no, we don't need to divide OLS with OLS Harvey. Generally, if we need to divide the OLS Harvey one with MLE, then we see how efficient it is. The efficiency test will be proven from here. So what happens here is that beta hat least square, we just need to divide this with this, and we see that if what is the efficiency ratio, are they asymptotically efficient or not, that is a question too, because we have, okay, are they asymptotically efficient or not, that is proven because we run 550 and 500 times. So 5 times they're not asymptotic, they're not t is not tends to infinity, 50 times t is not tend to infinity, but when we're doing it for 500 times, t tends to infinity. So 5 in columns, we combine 550 500 in t, combine, c is combine, it's not column, it's not row, it's just combine 550 500. So first study in the first one, t equals tk. For 5 we'll see they're not asymptotically efficient. For 550 we'll not see they're asymptotically efficient, but for 500 they will be asymptotically efficient if we just simply divide them together. We have three series, so we have three series of, we'll have three series of for and we'll have three series of, you know, estimations, or OLS estimations, all of the estimations, three series of them. So that was pretty good and important. Then comes next problem, relative efficiency of maximum likelihood and least squares.